Okay, back on refraction. I think I've got a better idea now. There you have the relativistic slide rule, and I've set it with a B value of 0.6. Now, if this photon here was going into water, then it'll look like that, which is a bit of a mess, so I better get rid of that. And if it was going through, and by the way, that's the refractive index of water, 1.33 recurring. That's how I get my B value there. Now let's say it's going through glass. By the way, these are this is the material, these are the layers in the material. Each time it goes through, its wavelength gets reduced to this phase velocity. In this case it's 0.75, so it's gone from a phase velocity of 1 to a phase velocity of 0.75. And I'll show how the angle's changed in a minute, but let me just do glass. So, oops. So 1 over the square root of 1 plus the refractive index of glass squared. Okay, you'll see that these lines are slightly closer together, and you see that the phase velocity will have dropped from 0.75 to about 2/3. Okay, so let's just get an idea. B can't exceed that, which is just through the vacuum. See that this is the same size as, these are all the same size, these photons are all the same size. Okay, so let's say that, let's just watch it. So you'll see that as the material gets denser, you see that this happens. These lines get closer together. As the material gets denser, the phase velocity of the photon decreases and decreases. See, those purple circles are the photons in the material. Their wavelengths or phase velocities are dropping and dropping and dropping and dropping and dropping, and at this point they're just completely absorbed. So let's come back out. Okay, so where are the angles? Let me just make that 0.6 again, so that's water again. There's water. Just put that on here, and if you look closely, you'll see the see which photon turns into which photon. You can see that's actually this photon, and you see that laser, that green laser, is going straight through the diameter. It's the diameter of the that black photon there, and then that photon becomes this photon, which is smaller, which is a lower phase velocity. And you can see that this is the normal to the surface of the material, and so that's the angles. And just another note, if you want to get the critical angle, there is a nifty little trick where you simply take the proper acceleration, which is that one here there that I just highlighted, and all you do is you just slide it up to become the centripetal acceleration. So proper acceleration, you just slide it up until it's at right angles, and then you'll find that this angle will open up to become the critical angle. Which in this case is that. But in fact, what you do is you just slide this proper velocity here, which is proper acceleration, which is 1 over t squared. You just slide it up until it's at right angles with the group velocity, which is in line with, is parallel to the normal, and then divide by the phase velocity, and you take the inverse sign. That'll give you the basically it's just giving you the angle where in the case of critical angle, you're interested in the photon actually trying to get out of the material, so it's heading left instead of right, and so at the point, the critical angle, it can't actually get out of the material, so it actually reflects back into the material, and that's how photo optics works.